You will recall that when it comes to the conic sections, they're created as such. Consider any two intercept lines, pick one of the angles it forms, and look at its angle bisector. That will certainly be the angle bisector of the opposite or vertical angle. Now, if you take those two intersecting lines, rotate them off the two-dimensional import into three-dimensional space, about that central line of symmetry, and you're dealing with two branches of a mathematical cone. Now, if you take a cross-sectional slice with a plane just floating in this room, perpendicular to both the inkboard and perpendicular to the central line of symmetry, you're dealing with a cross-sectional slice, that's a circle. If you take a cross-sectional slice, perpendicular to the inkboard, but not quite perpendicular to the central line of symmetry, you're going to get an elongated circle, which we refer to as an ellipse. If you take a cross-sectional slice in such a way that it's perpendicular to my inkboard as well as parallel to one of the lines I used to create the cone, then you're going to get a cross-sectional slice that's a parabola. And lastly, if you take a cross-sectional slice parallel to the central line of symmetry, you're going to get two branches, which collectively speaking, we refer to as a hyperbola. Do not take this the wrong way. These aren't my definitions of the conic sections, but these four conic sections are special curves that can be visually illustrated by looking at two-dimensional cross-sectional slices of a cone in three space. There are some degenerate conics right here, passing through that point right here. The intersection is a point. Plane slicing as such, the intersection is a line. Plane slicing right on the inkboard is the collection of these two intersecting lines. So I do have some degenerate conic sections, but I'm going to restrict my attention to three of the four non-degenerate conic sections: the parabola, the ellipse, and the hyperbola. You've already studied the circle far too many times. Now, here's my formal definition of a parabola. Consider a fixed point and a fixed line. The collection of all points equidistant from a fixed point and a fixed line is what we refer to as a parabola. That's my formal definition. Now, to come up with a standard form for an equation of a parabola, I'm going to force my parabola to have a vertex at the origin, focal point is 0, p, which means directrix is at y equals negative p because the vertex 2 has to be equidistant from that fixed point f and the fixed line L. So to come up with a general form for an equation of a parabola, piece of cake. By definition, the distance between the arbitrary point on level P and the focal point, and the distance between the arbitrary point P and the corresponding point on a directrix, I'll call it A, must be the same. Using my distance formula, and again, using my distance formula. Getting rid of radicals and expanding binomial squares. Canceling what I can. Cleaning up. There is the standard form for the equation of parabola. If the vertex is at the origin, it opens up. If it opens down with the vertex at the origin, the equation is not going to change. It's just what people understand to be negative. If it opens to the right, it would look like this. And if it opened left, same thing, but the p is understood to be negative. Now, notice the significance of p. If you can get the equation of parabola in one of these two forms, p is the distance between the focal point and the vertex. And who really cares? Well, we do, because technically speaking, the wonderful reflective quality that a parabola has is the following. So there's a vertex. Consider focal point here. If you emit a projectile from the focal point to the parabolic reflector, it's going to reflect off the parabola parallel to central line of symmetry. Or how about throwing a projectile in this direction? I'll eventually hit the parabolic reflector and tend parallel to that understood central line of symmetry. Now, if the vertex is not at the origin, then look at what it looks like originally. So with the vertex at the origin, opening up or down, that's the standard form. Opening left or right, vertex at the origin, that's my standard form. If, however, the vertex is located at H, K, then the standard form becomes this. Here too, if the vertex is at the point H, K, the equation becomes such. Sorry, did I miss something? So, if you don't mind me saying, let's concentrate on these two standard forms where the vertex is not necessarily at the origin, because if the vertex is at the origin, we merely have 0 for H and K in either one of these forms.